Alright, hello everyone. So today we're going to study resistors in parallel. Now, as you've seen in math before, if we have two lines like this, okay, which never meet, so these are going to be two parallel lines, right? Two parallel lines. Now, resistors which are in parallel look similar in a sense, although the not meeting part isn't really true. So, with resistors, we have, suppose say there's um, one resistor, okay, like this. All right, now, and we have another resistor, okay, let's call this R1, okay, let's call this R2, yeah, 2. All right, so these resistors, now if I connect them, like this, okay, so as you can see, they are connected. They are connected at both ends, okay, as opposed to resistors in series which are connected at only one end. So these are connected at both ends, so these they're resistors in parallel, okay. So uh, they are in parallel. All right, so let's just say there's also a voltage source here. Wait, let's just say there's also a voltage source here, battery or cell. All right, so these two resistors are in parallel, okay, with each other, and it's not necessary that we have only two resistors in parallel. We could have a third one, or as many as we like. So suppose that there's another one, okay, um, let's say that's R3, okay. So now these three resistors are in parallel, okay, and we can have as many as we like. We can add as many as we like. All right, now as with the series resistors video, I'm going to discuss some properties of resistors in parallel, and we'll see that a lot of the properties are the opposite of what was with the series resistors. All right, let's see. Okay. And oh yeah, should mention this. The formal definition, and we'll talk about that more when in a future video. I hope that's released in this week. But as I've said, the requirement for being resistors in parallel is the resistors are connected at both ends. So see, all these three resistors, they are connected at both their ends. Okay, they are connected at both their ends to every other resistor, right? Okay, so both their ends are connected, in this, you could say, in this common area, okay, in this common point, right? We'll talk about more of that, nodes and etc. When in a future video. I hope that's released this week. So okay, actually, why did I erase that? So I'll still write that. So uh, two on both ends. All right. Okay. Now, as I said, I want to discuss some properties, and the first property is, okay, so to show that, first I'll talk about an analog, and it's necessary because the way we are, the order in which we are taught, suppose say these resistors in series and parallel, um, for to discuss this first property, we'd if I wanted to explain this fully, we'd need to know about electric fields and all, okay, in some depth, but we can simplify our discussion. So let's, okay, first I'll draw an analog here. Suppose say this is, suppose say this is just our earth, okay, ground. All right, now if we have suppose say some um, object, okay, some ball right here, some boulder maybe, and we raise it to some height, okay, we raise it to some height, okay. Now what is, okay, so if this is h, if this is h, what is the change in gravitational potential energy. That's going to be or change in gravitational potential energy is going to be mgh, your del h, you might write it that way. So anyways, that's our change in GPE. Okay, and so what I wanted to talk about is, okay, so for this change in GPE, did we need to know how we took the boulder from this position to this one? No, right? So I could have just lifted it straight up. Okay, I could have lifted it sideways like this. Okay, I could have even like gone up, even suppose say through the atmosphere, and then come back at this position. But all of these would result in the same change in gravitational potential energy, right? Okay, so and that is because the gravitational field, okay, we have a gravitational field, okay, of the earth all around us. So suppose at the surface level it would look something like this, and you might later learn that as if we consider it a sphere, it looks like radial. Anyways, so we have a gravitational field, all right, but I won't talk that much about it. And it is conservative, okay, it is conservative, okay, and that is the reason why no matter how we move, okay, so the gravitational field, it's conservative, okay, conservative, and it's basically, there's no need to be intimidated about this word. It basically says that the only thing, okay, for suppose say a certain mass, suppose say a certain given mass, the only thing that affects the change in energy, okay, the change in energy are the initial and final points, okay, from where to where do I move the object. Those are the only things that matter when considering what is the change in energy, okay. The path that we take, it doesn't matter at all. We could take any path that we want. All right, so all right, and well, we could also say there's we could say it in another way, that for suppose if we divide this equation by m, okay, you can also think about it informally, that so this is equal to gh, and well, for our given two positions, okay, suppose say if for our starting, for a given starting and ending position, okay, obviously this is going to be equal, and this is going to be sorry, this is going to be, yeah, constant, and this is going to be constant too, right? So we could say that the change in GPE per unit mass is is going to be the same, okay, given fixed starting and ending points, right? Okay, the same starting and ending points, the change in GPE per unit mass is going to be the same. That's just another way of saying what we said just a while ago. And similar thing happens with circuits, okay, similar thing happens with circuits, or the electric field to be precise. But anyways, so if suppose say I have, okay, so wait, let me return back to my parallel circuit here. So see, here suppose say all these resistors, okay, they are connected at these 2 points, okay, all of them are connected to these 2 points, okay. Now uh, like the gravitational field, the electric field, and the electric field is basically what makes any circuit operate, okay, with the electric field is basically what makes any charge move, or any current to pass through. So that's basically what's making the circuit work, you could say, okay. And like the gravitational field, the electric field is also conservative, all right. So the only thing that matters, okay, for a given charge, the only thing that uh, you know matters or influences what the change in energy is are the starting and ending points. Okay, the starting and ending points. So if this is my starting point and if this is my ending point, to go from here to here, okay, it shouldn't matter what path I choose, right? It shouldn't matter. I could go through this resistor, okay, I could go through this resistor, I could go through this resistor, and I could go through this resistor. It shouldn't matter. Okay, my for a given charge the change in energy should be the same. Okay, or like we discussed here, okay, drawing the same analog here, the energy spent per unit charge should be the same. Okay, the energy spent the energy spent per unit charge should be the same, right? Should be the same, right? But what is the energy per unit charge? Well, that's just the voltage, right? That's just the voltage. So what I was trying to prove, and I hope you got at least a fair bit of reasoning for why this is true, and it is that the voltage across each of these resistors, okay, or any elements that are in parallel, they're going to be same. Okay, they're going to be the same. So the voltage across R1, okay, if suppose that this the voltage of this battery is V, okay, so the voltage across R1 is going to be V, the voltage across R2 is going to be V, all right, and the voltage across R3 is going to be V, and if we connect any other resistors or elements with in parallel with these, the voltage across them are also going to be V. Okay, so uh, the first property, let me write that down, is voltage across parallel elements elements are the same, right? And you might notice that this is uh, exactly the opposite. Okay, exactly the opposite of the what was true for the resistors. Here the current was the same and the voltage was shared, and for parallel we have that the voltage is the same, and you might have already guessed the current is actually going to be shared. Okay, just the conditions flipped around. So we'll be getting to that in just a bit. Let me first merge this. All right, so next property is, and this is a bit easier to discuss. So let's say that the current across the current through this resistor is I1. Okay, across this through this one is, wait, I should use a different color for current. Okay, so suppose say this is I1. Okay, suppose say this is I2, the current through R2, and the current through R3, let's say that's I3. All right, and let's say this current, the total current, you could say, the one that's going, the battery or the cell is delivering to this set of resistors, that's I. All right, now, okay, what do we see? That this current, okay, it's splitting up into three of these currents, right? It's splitting up into three of these currents. You could, suppose say, think of it like this: is, say you have a large road. Okay, suppose you have a large road, and it breaks off into three other roads. Okay, it breaks off into three other roads. Okay, now any you know any traffic, suppose say a lot of vehicles and you could think about these even as the electrons that are flowing here. A lot of vehicles are going forwards, okay, through this road. Now some of them might choose to go through here, right? Some of them might choose to go through here, and some of them might choose to go through here. And well, provided they don't break any traffic rules and for some reason don't go off track, okay, they every vehicle must choose one of these, right? So the total number of vehicles here, okay, the total number of vehicles here uh, has to be equal to the sum, right? The sum of the total in these three paths, in these three roads, right? All right. So same thing here, okay, same thing here. The the current the current uh, the current I, okay, the total current that's being delivered to the set of parallel resistors has to be equal to the sum of the currents through each resistor, okay, the sum of the currents through the individual resistors. All right, okay, and for those of you who really want a formal proof of this, it's actually not that difficult, okay, it would just take a minute. So for that there's actually one axiomatic statement, well, not exactly axiomatic because this one is, I'd say, a fairly convincing argument of this, but still no one has been able to exactly prove this theorem like the conservation of energy. But charge also needs to be conserved, okay, in the universe the total amount of charge also has to be conserved, okay. So charge is conserved, that's the law of conservation of charge, okay. Charge is conserved. If you think about these vehicles as electrons, um, the charge needs to be conserved. All right. So, and if we think about, suppose, say, um, charge being conserved, the charge through the charge that's flowing through this wire, okay, must be equal to the sum of the charges flowing through all, the three of them, right? The three of the parallel resistors. So we can write Q, okay, the total charge equals Q1 charge to the first resistor, Q2 charge through the second resistor, and Q3 charge through the third resistor. Now we are not very far from this statement. The only thing is, this charge we need to consider it for a certain time, right, a certain fixed time, which is going to be the same for everything here, okay, because this circuit is operating, okay, at the same time, you could say. So if we just divide by t, okay, the time, so this charge flows for a certain time t, and if we divide by that time t, q2 by t plus q3 by t. Now what is q by t? That's basically the current, right? That's basically that total current I talked about, because this is the total charge, this is the time for which it flows, so this is that total current. All right, now same thing here, same thing happens here, okay. The current, the charge through r1, okay, divided by the time for which it flows, that's going to be the current through r1. This is the current through R2. This is the current through R3. Okay, so we just formally proved that the current through a set of parallel resistors or elements, the current is shared. All right. So let me write that down. The current. Let's see. Choose green. The current is shared. Okay. All right. Okay, so that's our second property, and let's move on. So the next thing on the agenda is, oh yeah, okay, like before, I think it would be a good thing to do. Wait, let me just check if I'm recording. Okay, good. So I think it would be a good thing to see what happens if we have some short circuit or some open circuit, basically a closed switch, or switch on or a switch off, okay, with our parallel circuit. So let's say let me redraw this. Let's see. So we have one resistor, All right, so we have 2 would be enough, and suppose say we have our cell or battery. Now, okay, let's say that we have a switch here. Let's say that we have a switch here. All right, okay, and well, for now, let's keep it open. Okay, let's keep it open, or this switch is off. Okay, this switch is off for now. So, what's okay? So this is R1, this is R2. What's going to happen? What's going to happen? Well, this voltage, let's say that's V. So the same voltage V is going to be applied across this one, be applied across this one, right? Okay, as we just discussed, the voltage across them must be the same. And well, if that's true, the same the same current, okay, must flow through them. Okay, no, sorry, not the same current. The current. Wait, let me pause. All right, what I was trying to say is, well, okay, so there is a certain current I1, say, flowing here. Okay? There's a certain current I2 flowing here, and some of them I is going to flow here. All right, that's fine and well. That's what we have been seeing until now, and well, just consider this. So we have this switch open here, and this is all that's going on. Suppose if it wasn't there, okay, suppose say just wait, just imagine if this thing wasn't there. Okay, all right, so um, what's going to happen? Is anything going to change? Well, no, right? No, because let's just see. So if we just remove this, okay, if we just pretend this thing doesn't even exist, so uh, well, the battery is unaffected, obviously. The same voltage across both of these. According to Ohm's law, like, it has to be the same current across. The current across each of these must be constant. Okay, it doesn't change. I1 is the same as before. I2 is the same as before. Obviously, the resistance isn't changing. That's why. And so the total current has to be the same too, right? The total current, since it's the sum of these, it has to be the same. We didn't have any current flowing through this anyways, because this was an open circuit. So what we see is an open circuit doesn't affect parallel combination. An open circuit has an open circuit or switch has no effect. Open circuit or a switch off. Okay, switch off has no effect. All right, but well, there'd actually be like, let's see. Well, let's first discuss the short circuit, and then I'll show what happens if some branch actually gets opened. But first, let's discuss what happens if there is a short circuit. So that let's paint this black and close this. Okay. Right now, if I turn the switch on, this becomes a short circuit now, right? So something really interesting happens. Okay, what we see is, well, what is resistance? Okay, again, resistance is basically an obstruction, an impedance to current flow, right? So um, short circuit obviously has zero resistance, or has 0 ohms, zero resistance. So basically it doesn't resist or obstruct current at all. Okay, so now the current from this battery, okay, whatever it's going to be, um, current always, when you have a parallel connection, the majority of the current, or the highest percentage of current, does flow through the resistor which has the least resistance. Okay, and you can verify that mathematically too. The lowest resistance would obviously, according to Ohm's law, since V is the same for all of them, would have the largest current. But anyways, something interesting happens when you have 0 ohms. Okay, it's short circuit. What happens here is no current actually would flow through um, the other resistances. Okay, the resistances which are not zero. Okay, it's like um, it's like, suppose, say, if, well, let's go back to this example. So let's say that these let's say these are the electrons. Okay, okay, which are moving forward, and they have three paths. Okay, now, okay, let's say one, okay, one of them, which color should I choose? Let's choose this one. Okay, let's say one of them, okay, here, let's say it's completely free. Okay, the other two, let's say they have some the drivers can see that there are some boulders here, but you can still pass through. Okay, you can still somewhat pass through. You can see an opening. Okay, and suppose, say, here too you see some obstruction, but you can still pass through. Okay, if you just uh, try a bit harder. But uh, who would wanna, right? Who would wanna actually go through these obstructions, right? If they can, okay, if they can, if there's I'll ignore the thing about destination and all, but if they can, everyone would go through the path which has no obstruction, right? Okay, nothing wrong going on there. So and nobody would go through these two paths, right? Okay, which have some problems in them. So there will be uh, no drivers or no electrons. Okay, going through these two. Okay, so same thing happens here. Okay, that was just an analogy. So but the same thing happens here. Where's my okay, so what happens is no current actually flows through um, when you have a short circuit or zero resistance in parallel with other resistors. No current actually passes through the other resistors. So this one is going to be, wait, sorry, so this one is going to be 0. Okay, this one is going to be 0. Okay, and all the current passes through this. Okay, okay, this short circuit. And you might wonder what the current actually is. Now, since we are working with all of this theoretically, where a short circuit or 0 ohms is possible, let's just figure it out, and then I'll talk about what really goes on in the practical. So here, I think you might already have guessed it, but so if we apply Ohm's law, suppose if this is I. Okay, same as this. Okay, same as this, because no current flows through these two, as we saw. So if this is I, it have some voltage B. Okay, even suppose say it's 5. Okay, so suppose say it's 5 volts. It can be anything, any positive number, and we have zero resistance here, right? We have zero resistance, right? So this is actually going to be an infinite amount of current. Okay, it's going to be an infinite amount of current, uh, but that's what would come out, since we're considering all of these ideally. Like, thin wires with zero resistance aren't actually possible. Okay, what would happen practically is, if you just fit a thin low resistance wire across other resistors and have some substantial voltage source here, this wire, obviously a very high current would pass through this. Okay, and then this is going to melt. Okay, this wire, this is going to melt. Okay, and that is why I'll make video on that later. But that is why they tell you to not connect ammeters in parallel with batteries or cells. Okay, because ammeters have really low resistances. Okay, and the same thing happens really. So very large current passes through, and then the ammeter basically gets damaged or bursts. All right, so that's why you shouldn't do that. Okay, so that's enough for discussing what happens when you have a open circuit or short circuit in parallel with other resistors. Now I'll talk about something a bit similar, but just something a bit a bit of a modification. Let's say that, well, can I just copy? Well, I'll just redraw that. That's not a problem. Um, Again, your voltage source V, um, your resistor, Okay, another one. Let's say we have another branch which has another resistor. Okay, it also has a switch. Also has a switch. All right. So we'll call this one R1. We'll call this one R2. We'll call this one R3. So what happens here? Okay, so the when this is an when this is open, okay, when this is switched off or an open circuit, um, really you'd have V across this, so you'd have some current I1, you have some current I2 right here, and you have some current, the total would be I, okay, total of I would here would be I this would be I1 plus I2, okay, so here I would be I plus sorry I1 plus I2. All right, not very different from what we just what we discussed with the open circuit a while earlier. Now something interesting happens when we close this, okay, when we uh, close this. So I'll erase that and we'll close that. All right, so when we close this, something interesting happens. This is well, the whole branch, okay, if you consider it, it's not really a short circuit, you still have this resistance. So now what you've effectively done is introduce another resistance in parallel. Like before there were two resistances in parallel, now there are three. Okay, so what happens, as like we discussed before, um, no, actually, yeah. So here you'd have a voltage of V. Here you'd have a voltage of V. Okay, and so the current through these two wouldn't actually change. It's not like the electrons just got completely free path. This is not 0 ohms. This branch is not going to be 0 ohms. So um, the currents are here. Okay, currents through R1 and R2 would actually be unchanged. Okay, so the currents here would be unchanged, same voltage, same resistance, so must be same current across so through these two. So the current is unchanged. All right, but can we say that there's no change in the circuit? Well, no, there is actually some change. There would be another current here, okay, through this resistance. This would have the same voltage as the total voltage or the other two, so it's all V. Okay, so again, you'll have, let me use a different color for that. So you'd have the same voltage as all the other ones, V. Okay, so some a certain current, and well, this certain current, then now we'd have a new total current, right? This total current wouldn't be the same anymore. This would now turn into I, let's say I prime. Okay, so this is actually going to be the sum of all the three currents, right? All the three currents. Okay, that looks a bit ugly. All right. Okay, and you can also think about opening this switch again. Okay, opening this switch again. Now it's open, let's say, uh, and you'd go back to what was before. These two currents are still unchanged, right? These two currents are still unchanged, but there's no current here and the total current decreases. But we can see something important happening here. What happens is, suppose say if whether we close this or open this switch, or whether suppose say this an open or short circuit could happen, an open circuit could happen because this resistor gets damaged. Okay, that might be another thing. But whatever happens on this branch, okay, whatever happens on this branch, whether this resistor gets damaged, or if you open or close this switch, it doesn't affect the currents on the other branches. Just if there's no case that there's a short circuit, but anyways, we're assuming there's not. Um, so these currents remain unchanged, and that's the thing. Generally we have, generally this is how, just a simplified model, but this is how the appliances in our houses are connected. Like if you have three bulbs in a room, if you have three lights in a room, they'll actually be connected in parallel. Okay, and each would have their separate switch. Okay, they'd be connected in parallel, and they each have their separate switch. All right. uh, So, and so, why is this arranged like this? Well, you can just freely turn off or on any one of them. Okay, suppose if I just want to turn this bulb on, I'll just close this switch or turn it on. Okay, so the other two would still be off. Okay, and say basically that's really convenient for us, and I don't think we can imagine that would be very inconvenient if these were connected in series, like suppose say if we had one bulb, another bulb, and a switch. Okay, a switch, and then we had our power source. Okay, this would be very inconvenient because if we open this switch or we'll turn it off, both of these would be off, and if we close this or turn it on, both of these would turn on. Okay, so we cannot use them individually. Okay, so connecting them in parallel allows us to use them individually, one or more at a time, depending on which switch you use. So that's really the biggest advantage of using connections in parallel. All right, so that is our third point. That is our third point that I wanted to discuss. Is so let's see, turning on or off branch slash resistor doesn't wait, sorry, affect the other branches. There'd be a certain change to the total current, and also how much power the your main power source has to deliver. But that's a different discussion, and that's really about it. The other branches are not affected, which is what we really care about. If their functionality isn't affected, that's why they can be used individually. I think I'm really blabbering unnecessarily here, but I hope my point got through. Parallel circuits are really useful this way. Okay? Individual control. So that's our three features for parallel circuits. And to just wrap up everything that we have learned, let's do a mathematical problem with parallel resistors. All right. So here I have. Let's see. I'll use this one. Really like this color actually, this one and the light green one. So I have some cell or this okay, cell or battery here. Suppose say that has a voltage of V. We don't know what it is yet, and we have a resistor of 4 ohms. All right. Here we have another resistor R. Okay, some unknown resistance R, and we have another branch which is in parallel, and this one there's a resistor here, okay, of 2 ohms, and there's also a switch here. There's also a switch, okay, here. All right, which is currently turned off, or open. All right, and we have some other info. The current through the voltage source, or the total current, is 5 amps. The current here is 3 amps. Okay, and this is when this is all this is when this is off. This is currently turned off. Okay, so now my question is, what is the resistance here? Okay, this unknown resistance and this unknown voltage. So just find the unknowns for now. That's my first question, so let's solve that. Okay, so let's see. As we know, as we just saw, the current is shared, right? The current is shared, or the total current is going to be the sum of the individual currents, right? So let's use that fact. So the total current here, as you can see, it's 5 amps. So 5 amps is going to be, well, let's just write 5. 5 amps is going to be equal to, the current here is 3 amps. The current here, let's say that's I. Let's say that's, well, let's say that's let's see. Let's say that's I, okay, for now. So that's 3 amps. That's I. Okay. And this one, obviously there is no current here. Okay, so this is because this switch is closed. Sorry, I mean off. Okay, or open, you could say. All right. So now with this, we get that current through our unknown resistance is 2 amps. Okay, this is 2 amps. All right. Now we have the current through that, and well, okay. So current through this is 2 amps. Okay. The Yeah, and we also have something else here. We also have something else. The current through here is 3 amps. Okay, the resistance here is 4 ohms. What's the voltage through this resistor? What's the voltage through this one? Ohm's law tells us that the voltage through that is, suppose let's call that V1. Let's call that V1. Okay, and well, I think you can already see that's actually going to be the same as our total voltage. But anyways, let's just calculate that for now. V1 is going to be this this resistance into this current. So 4 into 3, 4 into 3. That's 12, 12 volts, 12 volts. And like I said, the total voltage is the same as the voltage through all the other resistances, all the resistances. So the this V1 is the same as this V, right? They have to be the same. Okay, the voltage is the same across parallel elements. All right, so this is the same as our unknown V. Okay, that's the first one solved. Okay, and for the second one, well, if this is this, the voltage across this is 12 volts, the voltage across this also has to be 12 volts, right? This also has to be 12 volts. Okay, same voltage through all the parallel elements, resistances. So this is 12 volts. We have its voltage, we have the current through it, then we can easily find the resistance, right? So the resistance is going to be, Ohm's law tells us that this is V by I. So that's 12 over, the current is what? 2 amps, right? 2 amps. That's 6 ohms. 6 ohms. All right. So those are our unknowns. We just found our 2 unknowns. And just as a last part of this question, the second part you could say, is what happens if we now close this switch or turn this switch on? Okay. So if we switch it on, what happens here? Okay, what happens here? Well, one thing is these currents remain unchanged, as we just discussed. Whether this branch closes or opens doesn't affect these two. All right, it's not going to be a short circuit. Well, and what we see is, so this, the voltage across this is 12 volts, right? This is 12 volts, the same as the other ones, and we have a resistance of 2 ohms here. So current through this is 12 by 2, or 6 amperes, right? 6 amperes. All right, uh, everything here is unchanged, but there's actually going to be some change here. There's going to be an increase in current. We had 5 amps here before because of, these two adding up. They're still the same, but we have an additional 6 amps. So now we are going to have an additional 6 amps here. So that's going to be 11 amps. Okay, the voltage source now provides 11 amps. Okay, and you can clearly see that, this provides a higher current, and that's why it has to provide more power too. Okay, than before. You can calculate the change in power too if you like. So that is what happens if we turn this switch on. And well, that's the end of this lecture. Hopefully I've covered everything about parallel resistors, except I know I haven't covered equivalent resistance, and I do plan to in the next video that's hopefully going to come out tomorrow or day after tomorrow. Although I have been able to upload on a daily basis, I don't think it would be possible when my semester, the next semester starts. But hopefully, I can still upload. Well, that's something for much later. But I hope 150 videos in a year. I hope that's possible. It's still something far fetched, but I hope that's possible. All right. So, but for that, I really need some motivation. So, guys, please do stick with me. I know there's a lot of things that probably aren't satisfactory about me. I blabber too much sometimes, and I myself I'm trying to fix it, but maybe I make some things complicated where they shouldn't be, especially for beginners. I'm trying to make things more approachable, but it's like my brain's sometimes stuck on rigor mode, and I try to cover everything to the fullest extent, but that might not be the best way to teach these beginning topics. But I'm trying to fix that. Guys, please do stick with me. Okay, please do support me as much as you can. If you like this video, I mean, if you appreciate it, please do leave a like, subscribe, turn on the bell, and also if you have any suggestion, please do leave it in the comments. Or if there are any issues, please do also leave it in the comments, and I'll see you in the next video. So study smart.